So it's my pleasure to have Dr. Sreenivas Bhattiprolu for our talk today, for our session today, which is on deep learning for microscopy image analysis. He's our invited speaker, and on behalf of the ICI team, I would like to welcome him. He is the head of digital solution at Zeiss Microscopy. He is a trained physicist and a material scientist. He obtained his master's degree in physics from University of Hyderabad and his PhD in material sciences and engineering from the Michigan Technological University. He also was the group leader at Ohio State University, if I did not get this wrong. His team at Zeiss focuses on solving tough microscopy challenges by leveraging the latest advancements in technology, which are digital, and AI. He has more than 25 years of experience in the field of microscopy in a variety of fields, including life sciences, material sciences, geoscience, electronics, and semiconductor technologies. Other than his profile where he does science, he's also interested in being a geologist, and a word that I learned from his profile is he's also a petrologist, right? So it has nothing to do with petroleum, it has to do with somebody who's interested in rocks and stones and formation of that. So that was an addition in my vocabulary. So thanks, Srini, about that. Apart from that, he is a wonderful educator who simplifies some of the most complex concepts and present them with clarity. So if you want to learn more about Python step by step in relationship to image processing, want to understand how to incorporate deep learning in Python, do check out his YouTube channels, Digital Srini, as well as Apeer. He is a wonderful, wonderful teacher, and you won't regret that. So without further ado, I'll give it to Srini and let him present today's talk.
Thank you, Gaurav. Let me switch the screens here. Let me go ahead and present my screen. So I'm new to Zoom, and I use Microsoft Teams, but I think they're all pretty much the same. Okay, can one of you confirm that you can see my screen?
Yeah, you're good.
Okay. So thanks for the great introduction. So just to add to that, I like you just learned, I have 25 years of experience in using microscopy, and primarily I started this back in 1995 when I first started working with microscopes, and I'm a physicist and a material scientist, so most of the time I spent looking at samples under an electron microscope or an X-ray microscope. You may know that as a computer tomography, for example. And also for the last 4 or 5 years, I've been getting more and more familiar with life sciences, the field of life sciences. In fact, I pretend to be a great life scientist when there are no other life scientists around. So, but I know just enough to figure out, okay, this is the image, and this is the challenge that need to be solved based on the image. And after looking at all of these different types of images, microscope images, I started to realize the importance of machine learning. In fact, I got exposed to this machine learning field of machine learning literally not that long ago, 4 or 5 years ago, and got really fascinated by that technology. So that's the core essence of this. That's the core topic for this next 40 minutes or so. And the reason, again, why I think this is important, why I think biologists should learn about machine learning is the reason is what you see on the screen, right? So you can see how the number of publications in machine learning are exploding, I should say. If you look at this in 2020, there are like, in fact, when I compare that with the number of publications with the keyword microscope, in 2021, we may have more publications with the keyword machine learning than actual microscope itself. This means machine learning is becoming a very important, useful tool for biology, just like microscope. Yeah, just like a microscope, machine learning is another tool. Now, the reason why I'm using the term tool for microscopy is I don't expect biologists to be doing extensive research in this field. Of course, if you want to go into deep learning research, fine. But for you, this should be one of the tools in your toolkit to solve a problem, a complex problem that cannot be solved using a simple method. Obviously, the simpler the solution, the better it is. But if it cannot be done in a simple form, then of course, machine learning has proven to be a very promising technology that can address these. Now, let's talk about what machine learning is. What do I mean by machine learning? So we are all on the same page. I think we all have pretty much the same understanding, but it's very useful to be on the same page. It teaches the system to automatically learn without any explicit programming. I hear feedback. Someone can mute the microphone. Yeah, much better. So it's actually teaching the system the ability to learn without explicitly programming. What do I mean by that? Well, it's not like we are coding an equation, force equals to mass times acceleration, or E equal to mc square. This is not based on explicit programming or a set of principles, but it's basically more about, hey, here is the data I have, and here are the observations or ground truth. Go ahead and fit a model so I can use the model in future to do a task in an automated fashion. So that's what machine learning is. And the learning process begins with your data that's either labeled or unlabeled. And if it is labeled, it's called supervised learning. What do we mean by that? You have a bunch of images, and you painted on the images to tell the algorithm what the ground truth is. Hey, this is a mitochondria, this is a lysosome, these are lipid droplets, and so on in your image. And you supply that to the model, so it learns about these features. And in future, when you feed an image containing one of these objects or multiple objects, it is trained to detect those. So that's how the learning process actually happens. And it can also be unsupervised. Unsupervised is where you don't have any labeled data, but you just ask the algorithm, just find patterns. Just find patterns in here. This is like our clustering algorithms. You have data that falls into multiple clusters, and you're like, okay, just figure out, divide this into multiple clusters. Once you have the trained model, now you can use that to predict future data. And why? Because this way you can automate your data analysis. Just imagine having a black box, which is a trained model, where you supply your images, it automatically segments them. So it saves you a lot of manual time in not painting the pixels sitting in front of ImageJ or whatever program you sit in front of. So this is, in summary, the machine learning from our perspective. Again, the topic of machine learning is pretty huge. You can go into language modeling, you can go into many other things, but this is. Again, I'm hearing some feedback. If everyone can mute, thank you. So now let's see how machines learn. Again, I in my presentation, I'm not going to show you any equations, nothing. I'll explain in as much as I can in plain English, so you all understand the guts behind this deep learning. When you press a button, what's happening? Because my goal is to make sure you understand when you start reading a paper, because you're bound to read a whole bunch of papers, and a good percentage of them will contain machine learning type of information. And then I want to make sure you at least understand the concepts at a very high level. So when we learn, like if I give you this data and I ask each of you to fit this, draw a straight line, you all probably have done linear fitting at some point. So how do you draw a line? So maybe this is this looks good to some of us because there's a good balance between the error on this side, error on this side, and I'm doing, without knowing, some math in my mind, right? I mean, we always do this. That's what humans do. We identify patterns, we try to fit things, and this is probably an okay line. If I give this to someone else, maybe they'll come up with this, and right away we say, are you crazy? This is not the right way, because you see how all the points are on one side. And then, okay, there is a good compromise. This is not bad. There's a very good balance between data points right there. This is a great line, great fit. So this is how we learn. We do this math without our knowledge in our head. How do machines learn? Here we need to convert that, whatever is happening in our mind, into some sort of a quantitative value. So in this example, each data point is actual real data. The line is what our model is. This is what we're fitting it to. So what if I can find the error between each data point and the line? So if I draw a line from here to here, this is my error, because this is where my real data point is, and this is where the theoretical or our model is telling us. So if you can quantify this error and add up all the error for each and every data point, then that tells you overall what is the error for this straight line. You can do that for other lines also, right? So how do you, but you cannot just add these because this is on the negative side, that's on the positive side. You don't want the error to be canceling out. So we kind of square it. So the negative sign is taken care of. So if this is y2, y1, we do y2 minus y1, which is our error, and then square it. That's my squared error. And then you add the error for all of these and take the average, which is nothing but we just proved the equation for mean squared error. Yeah, mean squared error, this is what you do with linear regression. We just proved the equation, how you do linear regression. So it's y2 minus y1 whole squared is your squared error. And then you take the average, which is the mean squared error. Why am I showing you this? Because machines learn by looking at this mean squared error. The goal of the machine is to minimize this mean squared error. We call it the loss function. The loss function is any function or any equation like this that the machine uses to quantify the error of the model. So in this case, for linear regression, the best one would be mean squared error, because that definitely tells us how good our fit is. So it draws a line, okay, the mean squared error is something, and then it changes the line until it finds the minimum in this mean squared error, and that is our linear fit. This is how machines learn. So they need a loss function, like whatever it is that quantifies. If we are trying to classify images as mitochondria and lipids and something else, then the loss function would be something that tells us how accurate are we at guessing which what organelle it is. Okay, so this is how they learn. So now let's hope at a high level we understand what machine learning is. So now let's see in image analysis, where can machine learning make a difference? I'm just showing you a very small subset of what machine learning can do, but I picked a few of these that we encounter on a day-to-day basis, starting with classification. Usually refers to classifying an entire image. You have an entire image. Does it belong to a dog or is this a cat? Right? I mean, this is classification. And then segmentation, and I'll talk about a few of the other things. Just a couple examples for classification. When you look at the image, you say, okay, there are some this is parasitized. So this is infected versus uninfected. So this is classification. Or is this mitochondria or is this not a mitochondria? Is this a good part or is this a bad part from manufacturing point of view? I'm just showing you binary classification here. It can be multi. It can be, is this A, B, C, D, or something else, right? So that is classification. And another example would be segmentation. Segmentation is nothing but classification, except we're classifying every pixel. Does that pixel belong to this class or a different class? This is what segmentation is. So if you look at this example image, is that pixel corresponding to a dog or to sheep in this image? So this is what semantic segmentation is. So when you read a paper about machine learning and segmentation, you will hear this term semantic segmentation. You'll also run into something called instant segmentation, which is nothing but our regular segmentation, which is semantic segmentation, except in addition to each pixel being segmented, you also have each object being separated. So here you have a dog, and you have sheep 1, sheep 2, and sheep 3. So this is what is referred to as instant segmentation. And when you look at other applications of machine learning, you have image corrections and enhancements, for example, denoising. This is another major application, especially if you work with confocal images. So today I'm going to focus on two things. One, I'll get a little, not too deep, but a little bit into semantic segmentation, or just segmentation if you want to call it, and denoising. But we also have other things. For example, putting machine learning to use. So if you work with Zeiss Microscope, you may have worked with Zen software. In Zen software, we have a way of automatically detecting the holder and also the samples and the specific regions within your sample, and automatically detecting all ROIs so the experiment can get defined automatically. So this, again, saves tremendous amount of time, completely powered by machine learning and detecting objects. So these are some, and like I said, let's go ahead and focus on semantic segmentation or segmentation first, and then denoising. I'm pretty sure most of you know what segmentation is. You have done thresholding, and you probably have done watershed-based segmentation, or even machine learning-based segmentation if you have used ImageJ or Elastic or something else. But I don't recommend using machine learning, I mean, for little tasks. Yeah, so you have to use the right tools. So for example, simple tasks. I mean, here, what I'm showing you is how many parameters are required to solve your problem. And it's going in a very logarithmic way. But if you look at a simple example, this is a binary segmentation, very easy to segment whatever these objects are just by setting a Otsu thresholding, right? You can just say, okay, 0 is background, somewhere above 100 pixel value, go ahead and convert that threshold, that image, and you get this segmentation. If this is the case, then you don't even need any other tools other than Otsu or multi-Otsu. Well, you can think of this as histogram segmentation, right? I mean, 0 to 50, class 1, 50 to 100, class 2, and so on. And to do this, you only need a handful of parameters, handful of values that you need to tweak, which is basically your pixel value. But if you have an image that looks like this, I'm not even sure if you can see it from your side, but this is a computed tomography 3D data set, and you can see how the background is right there, but then you have real structures within this region, and not just one phase, or one region, one type of class, but you have multiple types of classes here that need to be segmented. This is not achievable using simple Otsu or histogram-based thresholding, so you need to resort to some additional values or parameters that help you solve this problem. And for that, there is something called traditional machine learning. So if you have done machine learning in ImageJ Weka, I think that's what it's called, or in Elastic, or if you, again, are a Zeiss Zen software user, it's called IntelliSys. This is where you paint a few pixels and then hit train, and then it gets trained, and you apply that training to segment more images. So here you're training about a few dozen to up to hundreds of parameters. But if the problem gets even more complex, if you look at this image, the background is extremely busy, and it's very challenging to isolate mitochondria against this busy background. This is where the traditional machine learning has reached its limit, so you need to resort to deep learning. So not every problem, well, every problem literally is solvable by deep learning. I can take this image, and if I have enough images for training, I can fit a deep learning model to achieve that task, but there is no point in doing that because you can easily do this with very quickly using Otsu. But there are some certain challenges that require deep learning. And deep learning means you are actually training millions and millions of parameters. And in the next few minutes, I'll attempt to explain why you have these millions of parameters. What do I mean by these millions of parameters? So you'll get a better understanding of what deep learning, what's happening when you're doing deep learning. But to be fair, these tools, like the deep learning, for example, they're accessible only to people who are researching artificial intelligence or computer science majors or advanced coders. You'll see a lot of advanced coders also in biology field. How do we make this accessible to a biologist who is focused on solving a biology problem? So this is where we developed a platform called Apeer. I'm going to briefly talk about it, and hopefully I don't have to do a lot of explanation in terms of how to use it. We try to make it as easy as possible. It's online. You can sign up. You can go ahead and start using it. So let's first understand each of these. I'm not going to talk about Otsu. I assume you know what Otsu is. I'm going to quickly mention the traditional machine learning and deep learning, and then let's go ahead and switch to denoising and understand that in the next 15 to 20 minutes. So starting with the traditional machine learning, I am focusing on this part, the traditional machine learning part, because based on my experience, about 90%, if not more, of images that I have seen can be easily segmented using this approach. Only a subset, very few, require deep learning, although we are pushing the limits of applications, we are pushing the limits of imaging, so you may see more and more images fit into this category of requiring deep learning. So for traditional machine learning, let's say you have an image and you have a corresponding mask. This is the raw image. Again, this is a computed tomography image. I don't have a equivalent life sciences image with multi-classes. That's why I'm using this. So in this image, just think of this as, okay, you have multiple classes. You have background, you have these bright pixels, and you have the dark pixels here, and you have this gray region, and you also have the dark region. I'm not sure how clear it is showing up on your side, another region. So for each of these, I painted the pixels, and each pixel value, in this case, value of, for example, 4, pixel value of 4 corresponds to all the bright regions that I have labeled. Pixel value of 1 corresponds to one of these dark regions, and so on. This is what labeling is when it comes to machine learning. When labeling or annotation, you're painting the pixels. In the back end, those pixels are converted to a value of 0 or 1 or 2 or 3, each representing a different class. So this is the ground truth I'm providing to the algorithm. So then I apply a lot of filters to your image. Again, this is the case whether you use Elastic or ImageJ, or whether you use Zen IntelliSys. There are a whole bunch of filters. Gaussian with sigma equals to 3, Gaussian with sigma equals to 9, and median filter, Sobel, Shar. You know that Gaussian is denoising filter, also blurs the image. You know that Sobel finds edges. So we are extracting, by applying these digital filters onto your image, we are extracting the features. We are quantifying the features. So when we apply Sobel, it tells us that, hey, there is a hard edge right there. So it knows that, okay, if there is a hard edge, it must be this. So by using features, you're trying to extract the information from the labeled regions. So it's going to look at this label and says, oh, in this label, this is the mean pixel value, and this is our median pixel value, and this is how the edges look like. This is how, when you smooth it, the image is going to look like, and all that stuff. And the response itself, let's say we capture it in a CSV file or an Excel sheet. Okay, if we apply Gaussian with sigma equals to 3, here is every pixel value that you're going to get, sigma 7 and median and all that. So once you capture this, this gets fed into your classifier, because eventually what your goal is to classify every pixel, not just in this image, but also other images, into one of the 4 classes that we just defined here. You see, that's the label right there. So what I'm showing you here is called random forest, but there are many other machine learning classifiers. Listen to the terms like support vector machines is another thing that you'll probably hear or read when you read some papers, but random forest is quite common. So this is nothing, again, this is very simple. It says, okay, at this pixel, at this feature, for example, if this feature is a median, and if the value is less than 10, go this path. If the value is greater than 10, go this path. And if the value equals to 10, go this path, right? So it's basically rule-based. And then eventually down here, it says, okay, if you come down this path, then that pixel belongs to class 0. Otherwise, it belongs to class 1 and so on. And then that's how the classifier works. So this is literally your traditional machine learning. The key thing it relies on is feature extraction, which means we have to define what features we need to be using. And you have to be pretty good at identifying what these good features are, or good digital filters are. So here I'm just showing you a few handful of digital filters. If my goal is to extract all the pixels from this zebra or define this zebra, if I align this around 45 degrees, you see how I'm getting some of these, but then the band, the width is too large compared to the size of these. So if I change it to this, you see how I can actually detect more of these bands. And if I change it to something else, I find more of these. So if you're good at feature engineering or designing the filters, you can say, oh, these are the best filters for this application. So let's go ahead and apply those, and then add a classifier to do your machine learning classification. So basically, good features or good digital filters that extract the features should highlight the useful attributes. Now, for complex data like the mitochondria, we may not know what these right features are. Otherwise, we would engineer our way into the segmentation. So for complex problems, the key is that we don't know what these right features are. So let's use deep learning where these features are learned via training. So in here, we are deliberately telling what digital filters to use. In deep learning, we start with some guess and let it train on the training data, and it ends up with the best filters that works for that specific problem. That's what deep learning is. Now, let me elaborate a little bit more on that. So if I have an input image right here, where you have a mitochondria, you get the pixel values and you feed it to what we call input layer. Just take the pixel values here and then call that input values. And then each input value is connected to another node. And as you can see in this case, I have 1, 2, 3, 4, 5, 6, 7 of these. Each pixel value, input value, is connected to all 7 of these. So these are all, they call it densely connected. Okay, again, another term that you probably will hear when you run into anything about deep learning. So what are these? Each one of these, think of this as an artificial neuron. This is where neural network comes into picture. Think of these as artificial neuron. To this specific neuron, it's getting information from each and one of these input values, except for this one, because I decided not to put it. So, but typically every one of these is connected. And this neuron does some math and says, okay, let me transmit that information to the next level. The next level can be another layer, and the next level can be another layer. This is exactly where the term deep learning comes into picture, because this can go deep. This is not just one layer. Yeah. So this is where deep learning is coming into picture. And finally, you have output layer, where in our example, let's say we only have 3 outputs. This can belong to either lipid or a mitochondria or a lysosome. So at the end of this, it's going to tell us this image, it's 92% probability that this is mitochondria, or 7% lipid and 1% lysosome or something. So this is the structure of what we call a densely connected neural network, or a fully connected neural network. And as you see, these multiple hidden layers are there to learn hierarchical feature representation. What do we mean by that? Maybe in the first layer, they learn about the edges. When the information gets to the next level, they learn about the combination of edges, which means some shapes. And when you get to the next level, they learn about identifying specific features. And finally, that information gets to output layer. So there is a reason why we have multiple layers like that. And because we looked at this, I just want to make sure you understand what a neuron is and what is happening there. Again, very simple math here. This is the structure that I just showed you. So let me repeat that here, a little zoomed in, so we can for easy visualization. So let's say these are all the pixel values, like x1, x2, x3, x4, x5. These are all pixel values. All of these are connected to this neuron. All this neuron is doing is just a simple math. It takes your pixel values, and then it takes these weights. Think of this weight as how important is that pixel value. If the weight equals to 1, it's probably important. If the weight equals to 0.001, it's probably not that important, right? So it takes this, each one of these is associated with a weight, and this neuron is basically doing simple math. It's just multiplying x1 with w1, x2 with w2, like multiplying corresponding weights. And then on top of that, it adds something called a bias, like another value. That's it. All this neuron is doing that and giving an output. If you think about it, if my input pixel values are, let's say 255, and the weight is like 0.75 or something, then you have something around like 200s. And when you add all of these, then your output could be anywhere from 0 to infinity. I mean, if the pixel values are 255 and you only have n number of these, then you can figure out what the value is, right, on this side. But my point here is the output of a neuron can be anywhere from 0 to whatever a large number is. But so to control that, they add something called activation. You say, okay, let me squeeze my output between values of 0 and 1. It can be anything. I mean, I'm just showing you a sigmoid type of activation, but it can be a step function saying anything below 0, just call it 0. Anything above 0, just make it 1 or something. So it depends. But the key point here is there is something called activation as part of your neuron. So the output on this side is literally a probability. when it comes out, because the values are between 0 and 1, right? So it's almost like probability. And now you can connect this to the next neuron, or you can connect this to the output layer or something. So this is exactly when someone says neural network, this is the function of a neuron. Take information and transmit that information by scaling it to some value. This is an artificial neuron, so hopefully you know that now. And now, finally, by the way, one thing is all the weights and biases. If you ask, where do we get these weights from? This is exactly what training is all about. It starts with some random weights, it trains it, and then it compares against truth. It's like, okay, these are all dog images, and now go ahead and predict, oh, this is 80% of them, you're getting it correct, 20% you're getting it wrong. So adjust the weights, do that again, adjust the weights, do that again, until you get some convergence. That's what deep learning training is. Now, another term that you'll hear or read is convolutional neural network, or CNN. This is pretty common for image processing. What that means is, let's understand what convolution is first. If you look at this small area, when you zoom in, you'll see that this is basically pixels, right? I mean, this is an image is nothing but a collection of pixels with some intensities. This can be 255 and that can be 0 and so on. So let's go ahead and depict a smaller region right there with pixel values right here. And let's pick a kernel of size 3 by 3 with some values in it. A convolution is nothing but you apply this to the equivalent pixels on your image. So this is 3 by 3. So I pick a 3 by 3 grid right there. And then you just do simple multiplication. -1 times 170, 0 times 245, and add all of this, you get a value of 394. At the end of your convolution operation, which is basically replace this central pixel with whatever the calculation is, 394. This is how any digital filter that works in the spatial domain works. You have a kernel. So for example, if you have a Gaussian, when you apply Gaussian smoothing or Gaussian denoising, there is a Gaussian kernel that you apply to your image. And it gets applied, it moves to the next step, which is we call stride. If it moves by one level, and then it moves, and eventually you would end up with a smooth image. And for Gaussian, you know the shape, and this is how the kernel looks like. And we are dividing by 273 because when you add all of these values, they add up to 273. And by dividing by 273, you're normalizing it, and you're not adding information to your image. You just want to apply this kernel. This is literally how digital image processing works. And this is a basic convolution operation. Now in a convolutional neural network, now there goes the complexity. Your input image, you apply a convolution right there. You see how many convolution filters I have? Think of this as Gaussian filter, median filter, Sobel filter, whatever another, how many ever filters you have right there. You convert your single input image into that many outputs, which is feature responses. And then you connect this output to the next layer, which is also a convolution. Again, by definition, a convolution means you have a kernel, like I just showed you, and then it acts on your image to generate filtered images. And how do you define that convolution kernel? With what values? This is exactly what gets learned during machine learning. So as you can imagine, this part where we have images and convolutions, this is there to generate feature maps. This part is there to help us classify. A combination of this is called a convolutional neural network. It can be a fully convolutional neural network, which means you don't have the classification, you only have this part. And for segmentation, we often use only the convolution layers. So just like the key point here is, just like the dense layers, these convolution layers also have weights and biases, which is nothing but your, the kernels. And they're adjusted during the training. And at the end of the training, you'll get the filters defined. And this is exactly why we call this feature learning. We are learning the features and we're not engineering the features. So the best convolutional neural network for image segmentation, this is an amazing paper. You can read this UNet convolutional neural networks, and this is for biomedical image segmentation, but it also works for any type of semantic segmentation. And the way it works, again, at a high level, I'll explain what this is you have your input image of size 256 by 256. You apply convolution to generate 64 filtered responses. To that, you apply another convolution, 64 filtered responses, and then you decrease the size of your image and then you do these operations. So as you go this path, the image size decreases, but then you get a lot of features. And as you go back up from smallest resolution back to your original image resolution, you actually get a segmented image. I know that sounds very abstract, but again, on Apeer micro videos or on my channel videos, I have spent a lot of time trying to explain this. So please go ahead and learn more if you're interested in learning more about unit for sure. But I just want to make sure you understand that this is why it is called a unit. It's in the shape of U, and this is nothing but convolutional filters where you're applying a convolution operation and a convolution where the weights are learned. How do you get your hands on this? I'll talk about that in a minute. Like if you don't know how to code, I'll talk about that. And I'll also browse through denoising in the next couple of minutes. I just want to make sure you have enough information so you can go and Google search and learn more about it if you want. When it comes to denoising using artificial intelligence, noise to void is probably the best, especially if you're working with confocal images where you cannot obtain a cleaner version of your noisy image. If you spend a lot of, if you collect an image at higher laser power, or if you spend, increase the dwell time, pixel dwell time, or average it, you can always get better images. But for live cell imaging, you may not have that luxury sometimes. So in those cases, noise to void can be extremely useful. And it works under the premise that signal has structure and noise does not. In our image, noise is random. That's what it's assuming. And signal, I can predict a pixel by looking at the surrounding pixels. But when it comes to noise, I cannot predict the pixel by looking at the surrounding pixels. That's the premise it works under. And let me just switch to the next screen so it's easier for me to explain. So you look at a smaller area. This is the patch it's looking at, and it replaces the central pixel with some random pixel that it identifies and uses this for training. And that way they claim that, okay, this is like a blind area right here. So it doesn't learn about the, noise, but it learns about the structured regions by creating a blind spot right here. So that's the core principle. Again, the paper does an excellent job talking about this. So please, I definitely recommend learning more about it by reading it. And they have done a great job by comparing against other state-of-the-art approaches right there. And this is, the training part is slow, but applying it is pretty fast, even compared to some of the other techniques. Here is, let me just show you the comparison right here. Here is the original image. There is the Gaussian. You know that Gaussian is going to denoise. And here is another one. And this is the noise to void. Again, please remember that noise to void is not a super resolution technique. It's not going to give you better resolution. It's going to denoise the image as is. So here is a data set that I have denoised using this approach. Pretty easy. Again, no need to code. I'll show you why you don't have to code. Because we included those as part of our Apeer platform. And the whole motivation behind this is to make these advanced image analysis tools accessible to everyone. So you can automate your analysis. And this is, again, a free platform. It's available at Apeer.com. Go ahead and sign up, and it's free for nonprofit. I'm not sure if any of you are currently a biotech startup or know someone from biotech startup, but we started a new thing where we are designing Apeer for biotech, and just to make sure we can speed up the biotech, the startups, especially the startups, their image analysis time and everything, because time is money for everyone, but especially for startups where they don't have the luxury of a lot of money in the beginning stages. So please do let me know if anyone wants to learn more about that part. But when it comes to academia, Apeer is free. And just to give you a high-level overview, so you don't, so at least you get some familiarity. When you log in, you see that, okay, you have a dashboard on the left-hand side. You see the community content. This is the public content that's developed by the community, shared by the community, or someone from our team, from Apeer team. Either way, everyone sees this. The My Lab part, no one sees that. Only you can see it as a user. This is obviously, there's something like your bank account. You log in, you see your own stuff. So your own workflows, your own results, your files, and you can store up to 100 gigs on the platform. So this is only available to you, accessible to you. And machine learning toolkit, these are the deep learning tools for segmentation. And again, only you can see your own content right here. So you can upload your images, you can train, you can segment, and what's powering behind this is our unit that I just talked about, except a modified version of unit. We made it scalable. Just to show you how you can run a denoising algorithm. So let's click on public workflows and go ahead and search for denoising. And it should bring up a few of these. And these are all workflows I'm looking for, meaning not just a single task, but like an end-to-end workflow. Let's look at let's look at machine learning.
Hola, mi vida, acabo de ver que está lloviendo. ¿Cómo vienes?
I can't.
You should be fine. Sorry about
Okay, yeah. So as you can see, I'm not sure where we lost. Yeah, so if you see, this is a connection of different modules, and make sure you always select the latest version. And all you need to do is go ahead and drag your images. So here in this workflow, we are using noisy images, and we're using them to train and then to segment. Yeah, so that's the process. Now, if you just have confocal images, you don't have to train. We already trained a model on hundreds of noisy images. So this is what you need to look for, LSM. You see only one module, which is pre-trained. Go ahead and upload your image that you want to denoise. And by the way, this is all in the cloud. Again, if you have Zeiss's Zen software, you can download this module locally, and you can run it locally if you want. But again, this is in the cloud, means you can use any browser, and you can go ahead and use that, access this platform. So and when it comes to segmentation, very similar process here. You can just select, okay, you want semantic segmentation where you're segmenting this, or you want to do segmentation followed by separation, where individual objects are separated, and hit next. But obviously you need to go ahead and annotate. So first you upload your images, you annotate them by saying, hey, this is my class 1, this is my class 2, or whatever, the classes you want to label them as. Go ahead and label them, hit train, select what type of training you want to do, and then go ahead and segment your images. So these are two examples of where we took this deep learning and made it accessible to anyone. I want to say biologists, but these tools are data agnostic. They don't care, if you're a biologist or not. They just care about your images, but definitely make it accessible to researchers so you don't waste your time, painting these pixels forever. If you are painting your pixels, that should be for labeling, so you can train an algorithm that can be used for the rest of your research. So just before finishing off, just a quick screenshots. Here is a binary segmentation where the membranes in this case are segmented. Here is a binary instance segmentation where each object is segmented in addition to just the mitochondria being identified here. And here is again a multi-class semantic segmentation. So we have not just a binary problem, but many different types of classes. In case you're curious, this is again a oil and gas type of rock, and this is a sandstone. Like you have quartz right there, and the dark area is what the oil and gas engineers are after, because this is dead animals, or this is the organic matter, and the pores is where the hydrocarbons are sitting, whether it is natural gas or whether it is oil. This is where it sits. And the more pores, the better. The more connected they are, the better. So this is a challenging problem for segmentation. But again, with machine learning, you can definitely easily automate this entire process. So with that, I think I talked for about 45 minutes or so, but it's now any questions you have about anything, please go ahead and unmute your microphones, and please shoot the questions at me. Thank you.
All right, thank you so much. That was really great. A lot of the people asked questions because I'm sure a lot of people will have questions on this, because we went over Cellpose, we went over StarDist, we looked at the application side, but this is the heart of what's happening behind the scenes. So please feel free to ask Dr. Srini any questions you might have. Then we already have one from James, and he's asking, can we use Apeer to train and develop our own modules, more specifically on 3D image stacks?
Yeah, so Apeer is basically, if you look at this screen, this My Lab part, these modules are, you can actually create your own modules. The only thing is you need to know coding to create your own modules, right? I mean, they don't magically appear. To create workflows, it's pretty easy. You search for what modules you want to cobble together, you put it together, and this is easy. To create a module, you need to know Python, or, I mean, we use Docker containers, but if you know Python programming, you should be pretty good to start. Even if you are, let's say, not absolute beginner, but you have familiarity with Python, you're a bit comfortable, then you should be able to follow the guidelines on Apeer and create your own modules. And definitely you can create, these are basically small computing plugins, if you want to call them. So it can be for 3D, it can be for 2D, it can be for anything. So yeah, the answer is definitely yes.
So I have seen most of the training are done with a single like two-dimensional images, many images. Right? So I have like many brain images, like 3D brain structure.
Can you repeat your question? We cannot hear you well.
Yeah.
I type in.
Yeah, it's hard to hear.
Can you please put that in the chat box, because we are having difficulty hearing you?
Yeah.
So while
meanwhile, while that's happening, just want to show you, I just opened Apeer right there just to show you the modules right there. You can actually add a new module and you can give it a name, whatever the name, and you can select, okay, what template do you want to use? And once you create a module, then it gets automatically built in the cloud. And then once you have let me pick one. Yeah, this is my module right there. And once you have this, you just need to go down and follow these, copy the code to local drive, generate the specification. So once you follow this, you will create a module that has the right interface, like user interface. What do you want user to input? It's incredible. It makes everything pretty straightforward. And these modules, no one can see that I have them. I mean, no one can see that I have my test module, but if I'm so proud of it and I want to share it with someone else so others can use it, I'll just click on manage shares and I'll just share it with other users. Right here, I have multiple accounts, as you can see. I can just share it with other users, or I can just go ahead and publish it, at which point it comes to our team and we assess whether it is safe, whether it is doing what it is supposed to do. And after it goes to the quality check, then it gets published and it shows up under public modules here. But you can definitely create your own modules like I just showed you. And as you can see, someone else is already sharing a bunch of modules with me, so I can use them here.
So the follow-up question was, can we specifically use this on 3D volume stacks and not just the image stacks when it comes to Apeer?
So when it comes to, I assume the question is related to machine learning in that case, because when it comes to just public modules, workflows and everything, you can design anything you want, right? I mean, you can create modules for 3D volume stacks and so on. If it is about machine learning, you can definitely, I mean, I have volume stacks right here that you can, but what we have on the platform segments one 2D slice at a time and puts it back together, so you have a 3D volume stack. So we are not using 3D kernels because that requires tremendous amount of memory. So this is, let's see, am I opening the right one? But yeah, the answer is yes. And also, if I go to my modules right there, you'll probably see some work right here, Bootstrap 2.5D predictor. This is the work that we are doing in collaboration with NIH, where they have developed a 2.5D approach for volume stacks, where you segment something in XY and YZ, and the quality of the segmentation is equivalent to doing a 3D segmentation. So once these are tested, we will release that onto the platform. And of course, you can use that approach if you prefer that. But based on my experience, the 2D slice by 2D slice does a great job, unless you're trying to segment neurons that are going in one direction, where 3D kernel definitely helps. Yeah.
So is it possible for us to kind of look at an example in future with this bootstrap method? Because that's something very unique in terms of how you do the annotation, which is kind of unheard of. If there is a video that you can create for that, it would be pretty great.
Yeah. Once we get this, the whole point, the reason why NIH is trying to do this is they developed something incredible with a lot of training data and everything, and they want this to be used by others. And right now, unfortunately, there is no single means of getting to microscopy users in a digital way. Like, okay, you have something and then someone publishes a paper and there is some GitHub code. How many people can understand GitHub code and interact with it, right? So there is no easy way. This is exactly why they approached us. And that's exactly why we are building these, so to make sure that, okay, now users can actually go ahead and use them just like a tool. So once this is published, of course, we'll add description for every module. We have descriptions that we add. For example, I don't know, you see all the description, which should be pretty comprehensive, if not a link to a video explaining how to use it. So we'll definitely get in touch once that happens. Other thing I want to also mention is once you have a workflow that you want to execute, for example, I have an object tracking end-to-end workflow where you can kind of, if you have a time series, you can track these objects and it provides you a report. And if I want to run that, I'll just go ahead, open the workflow and hit /batch run right there. And it says it's invalid because I don't have any input defined. But anyway, when I click this, it executes the workflow in the cloud. Now, we also have something that we don't enable for everyone. We enable for select people depending on the need. But please think about this. If anyone, if you have access to high-end Linux machines, for example, with GPUs, then if local execution is enabled, I can actually connect my Apeer account to a local system, and then go ahead and when I run the workflow, I can just go ahead and select, run it on my system 1, run it on system 2. So I can now decide where the computation happens. So when I click on this, I can just say, okay, run locally and create where. Right now I have 0 systems running. So, but this is another thing that you can benefit from. Again, we don't enable this to all accounts because people may not know what's required on the local systems. And you click it and then it doesn't work, and it's not the right experience that you would like to have. Any other questions?
So I will jump in if nobody else has a question. With regards to the convolutional neural networks, when you mentioned the whole convolution part where we can apply different kind of kernels, could be Sobel filter, could be Gaussian filter, and so on. Mm-hmm. If I was to take an image and apply all those filters, I would not be able to understand what the heck am I looking at the end of applying all those filters. How does, let's say if it's a UNet kind of a structure, how does the system or the filter figure out what's the final image that you are looking at after application of all those filters or n number of filters? Or is that where the weights and biases come into picture?
Yeah, in deep learning, this is where, so that's a good question because no one thinks about this, right? I mean, you have your input and you have your input masks. So I have my annotations, like for example, I may as well work on this. Do I have it here? Yeah, I have my input mask and I can basically say, let me add a class 1 or whatever, space. And I say, when I do this, when I actually paint this, I'm telling the system that this region belongs to my class 1. Okay, so that part is clear. Now, it looks at when we're defining our deep learning, we are providing it 2 things. We are providing it with the raw images and then corresponding ground truth, which is nothing but the mask that I'm going to define right here. So this image goes through all these weights. Initially, the weights will be randomly assigned. So the filter responses mean nothing. But at the end of this, you see how it classifies that as either, just a second, I think this probably makes sense. If I go back, you saw how the final layer is the output layer, right? I mean, this is, yeah, I think this one explains it. The final layer is the output layer. So here it's like, okay, is this a lipid or a mitochondria or a lysosome? So initially it may come up with a lipid as 90%, which is wrong in this case. So it this is where the loss function comes into picture. It looks at the loss function and says, hey, that is wrong because your ground truth, you told me this is mitochondria. But with these weights, it's coming up as lipid. So let's adjust the weights. And how does it adjust the weight? Again, another term to introduce is called back propagation. It adjusts the weights in the backward manner, and then it does this exercise again. And then if the accuracy of mitochondria goes from 0.1% to 5%, then it's like, oh, I'm heading in the right direction. Let me change the weights in that direction until it comes up to whatever the maximum accuracy right there is. So the ground truth that you're supplying is used to validate against right there. And the images are going through these filters where you get the filtered responses. And by changing the weights, you're in a way learning the right filters for that specific task.
No, wonderful. This is very helpful. Thank you.
Yeah.
And I want to apologize to everybody. I sent out a wrong link this morning, and that's why we had people trickling in late. If people will be looking at this seminar, is it okay if they contact you through your email if they have any further questions once they watch the video?
Yeah, of course.
Right. Thank you
I
so
have
much.
one quick question.
Uh-huh.
Can you hear me?
Yeah.
So there is also the platform called ImageJ. Are the modules exchangeable with your Apeer one or no?
No, not with DeepImageJ. I mean, we are trying to make ImageJ plugins work with, in fact, you can wrap ImageJ plugins into Apeer. Our modules are exchangeable with something. NIH has also started some initiative around this. And we have a constant exchange to make sure that they're interchangeable, like interoperable, these modules, so they don't get reinvented. But the technology that we are using and the technology that NIH is using is the same. ImageJ, I should admit that I'm not very familiar with DeepImageJ. ImageJ is primarily Java-based, and more things are towards Python nowadays. And but to answer your question simply, at this point, the module, you cannot just take our module and just work with DeepImageJ or something. Yeah.
All right, thank you.
Yeah, we use Docker technology. So anywhere you can run Dockers. In fact, you can download our modules and you can run it on your Linux or Windows system as long as you have Docker installed. And Docker, in case you don't know, it's a container technology. Think of it as a virtual machine, except in a virtual machine, you have the entire operating system that you need to boot up. In a Docker, it's a lightweight. So you don't need, you have the overhead of all of these. So in a Docker, you have the Python and you have your code and you have all the dependencies. That's it. That's a Docker container. And it is portable. You can take it anywhere. So if ImageJ ever runs Dockers, then of course you can expect this to run there. But yeah, that's basically the answer.
And you also mentioned so I'm from a university, so anything with academic is free for the Apeer user.
Yeah. For academic purposes, we want to keep it free. Definitely, it is whatever you see on Apeer right now is free for sure for academic.
All right, thank you.
Yeah, so give it a test and see if it really works for you. And definitely, machine learning toolkit will. I mean, there is no tricks there. It definitely works for you. I'm not saying there are tricks with other things, but the only thing I want to mention is if you really want to create your own workflows, then you need to know, oh, this is the first, just like ImageJ, right? I mean, you know, okay, this is the first thing you do. What should you do next? And why you should be doing that step next, and what step you should be doing next, right? So if you know that, then you can go ahead and create a workflow easily. But initially, it takes a bit of experimentation to figure out, okay, what module goes after this, and go ahead and add a module, I don't know, whatever the distance transformation map, and then connect these two. And so this is, initially it takes time, and you can test this by running one module at a time to see the output and build it. But once you're done, the whole point is automate it for future.
Right. So yeah. So I was really specific trying to figure out, because we are working on something to take a 3D confocal brain, the Drosophila brain, and we identify the degeneration as in terms of holes, and we're doing manually. It's currently like we go through one brain, we'll click on, you know, where is the holes, where is degeneration. So I thought this could be perfect for machine learning and then automated analysis.
Yeah, that sounds like a segmentation challenge to me. And for that, I would basically just go to annotate, create a new data set, give it a name, and go ahead and say, okay, which one do you want? Like, okay, let's say I want semantic segmentation, and it creates that, and go ahead and add your images here. And once you add your images, you can open them and start annotating. And we recently released partial annotations in deep learning. Traditionally, you have to annotate every pixel in your image. This takes too much time.
Right.
So we have partial annotation, which means annotate certain small chunks. And if you have a 3D volume, my recommendation is if it has like, I don't know, 500 slices, go ahead and pick every 50th slice and then start with 10 training images and
Right.
see how the result looks like. And if it's not that good, see where it fails. Hey, it's actually picking up more background. So let's add more background annotations. And a couple of iterations later, you may have your model, trained model.
Okay. Thank you. Yeah, we'll give it a try.
Yeah.
All right, so we are more than 5 minutes over 5. I want to thank Dr. Bhattiprolu again. Thank you so much, Srini. Really appreciate you joining us and helping us understand this field and the heart of the field in general.
No problem. Thanks for hosting me.
All right.
Yeah.
Bye, everybody.
Thank you all.